because at the end, I'm just proving something for commutative diagrams that has a feeling of like star autonomous categories, but my motivation is definitely geometric. And without the motivation, I don't know, this problem was motivated by me struggling to prove that diagrams commute. So I will explain some of the motivation first. So let X be a nice space. So often this, topological space, for me, these are going to be varieties. And I'm principally interested in a gadget that we associate to such a space, which I'm going to denote SX, which, just for completeness, I'm going to say what it is, but don't worry if you've never seen this before. This is the constructible derived category. Derived category of sheaves. So this is sort of in the same vein as what Marco talked about on Monday. So for us, this is just going to be a category which encapsulates a lot of topological information about our space. So yeah, so like even if you sort of, without getting into the construction, one can still sort of motivate this by saying that it encapsulates things like the cohomology, the homology, compactly supported homology, like you can talk about Maya via torus, like all of these basic algebraic topological lemmas are all encapsulated in this single object. And most importantly, like, if we just got a category for each space, that wouldn't be that great. But for a map, we actually get a lot of functoriality out of this setup. So we have a lot of functors between these categories. So there's two going forward, which we call F lower star, F lower shriek. And then there's two going back, which we call F upper star and F upper shriek. So yeah, now I'll indicate how you can get some of this topological information. So for any space, we have a map, the terminal map to the 1-point space. And so, and I'll say these categories are also monoidal. I'm not going to be using that in this talk, but like there's a bunch of structure on this. And so because they're monoidal, we have like a unit object. And if you push forward the unit object via this map, this lives in S of a point. And one can show that this is equivalent to the category of, graded vector spaces. So this is the one thing that I'm going to tell you what this category actually is. And the point is that, this is a graded vector space. What are its nth pieces? If your space is X, the nth pieces of this are the cohomology groups of X. If you take this thing, these are the compactly supported cohomology groups. And there is a similar canonical object which will give you the homology groups and the what's called like infinitely supported homology groups or Borel-Moore homology groups. Those also come from this just via the terminal map. And so this is also a fantastic place to talk about Poincare duality that has a very, very nice description in this framework. And lots of geometric questions are not necessarily answered, but it's very, very clear thinking in this perspective of how you should answer them. Okay, so, but for us, this is a category, and we have a bunch of functors between them, and we've got some adjunctions between those functors. So we've got, this is left adjoint to this, and this is left adjoint to this. And of course, if we compose these maps, we have coherent isomorphisms between the compositions of any of these functors. So these are all, I don't know, weak two functors, or like basically this assignment should really be thought of as we've got a category here, and we're mapping it to the two category of categories. So there are coherence isomorphisms between all of these different functors. Now, one thing which we have is, say we've got a map of spaces, so X to Y, and we take the pullback, then we get G prime, F prime. Then one important thing that we have in this setup is something called base change. So what this means is that we have a canonical isomorphism from you push forward, and then you shriek pullback is the same thing as shriek pullback and push forward. So basically, whenever you have a pullback square, you're allowed to go diagonally if you go push forward, pullback, or pullback, push forward, as long as you remember that your stars and shrieks have to be different. Now, if I had more time, I would probably want to say what this means geometrically, because this is like very, very important from a geometric perspective. But for us, we can just think of this as very nice compatibilities in this formalism. Now, I've got upper star and lower shriek, but it works for all combinations of these. As long as so you could lower star push forward, or you could lower shriek push forward. Yeah, but it's basically going diagonally in a pullback square. Okay, and what else did I want to say about this? So, oh yeah, and so there are certain times when F lower star is isomorphic to, F lower shriek is isomorphic to F lower star, or F upper star is isomorphic to F upper shriek is isomorphic to F upper star. Now, these, from this formal perspective, who knows what these mean, but these are incredibly important geometrically. This is like saying that you have an open inclusion, or maybe a covering space, and this is saying that a map is proper. So from geometry, those are both incredibly core fundamental terms. And from this perspective, it's just, we can maybe do extra things, because if we knew that our F had F lower star and F lower shriek were the same, we would have something like this that works for shriek and shriek, for instance. Okay, so this is about all the formalism that we need to go in. There is a lot to these categories, which I won't be talking about. In particular, there are apparently 6 functors. You may notice I've given you 4 of them. And in fact, I'm saying my result at the moment only works with 4 of them, in that I haven't yet pushed it to work with the full picture. But I think it's still interesting. And basically the point is, I live in this world, and I was really struggling to prove that diagrams commute, especially when it feels like it should be easy, which I'm sure is something which people can relate to when you're just like, okay, great, now I just got to show a certain diagram commutes. And then you sit there and it's like, oh, this is more annoying than it should be. So I want to give the setup for the theorem which I'm trying to use to make my life easier, which is basically that all diagrams built out of these base change maps and composition isomorphisms. So for instance, F lower star, G prime lower star, isomorphic to G lower star, F prime lower star. So this would be like a composition isomorphism, and this would be like a base change isomorphism. Basically, I want to prove that all diagrams built out of these isomorphisms commute. So we can see there's a lot more diagrams in this formalism than just this. For instance, you'll have units and co-units, and those genuinely do pop up and are relevant. But just for now, I want to prove something that says all diagrams built out of these and these commute. Okay. Any questions about the set? What? Yeah, so for instance, like say, what is it? Not sure if I want to draw it, but say you have a cube. Okay, yeah, here's one. So like for instance, say you're looking at Homs, F lower star, G shriek, whether you could interpret this as an object or you could just interpret these as functors. Then you could say, okay, and say F is proper, which means F lower shriek, G lower shriek. Sorry. Let's say we want to compute Homs between these two things, or potentially evaluate on a single object. By adjunction, this is, G star. And then by base change, we can swap the order. Shriek. And then, I don't know, maybe we pull that back over. So for instance, this is some isomorphism that you could do, which is just an isomorphism. And this may come to you from a geometric problem, and then you say, great, what if I want to take open pullbacks of these things? So I want to show that this whole picture commutes with taking open pullbacks, which you would want to, like open pullbacks are very natural. And then you could have a completely different way, which would start by saying, okay, take an open pullback and do a different operation, or take an open pullback at the end. And then all of a sudden, you've got quite a large diagram with a lot of adjunctions, and it's not clear why it commutes. Yeah, and like this is the example that sort of, made me want to do this, like proving that convolution algebras localize well in a formal way. Okay. Any other questions? Okay. All right, so I'm not particularly well versed in how to prove coherence results. I think the strategy which I have seen before is build a simplicial complex and then show it's simply connected, or that its pi2 vanishes, which is actually not what we're going to do here. This is a much more down-to-earth combinatorial thing that sort of, like, given such a diagram built out of this stuff, this would actually give you a recipe for showing that it commutes. Like, it's a constructive algorithm, I guess. Okay, so what we're going to start off with. So this doesn't, I need some qualifications. So say we've got a bunch of maps from xi to y. And then, so we could say x1, x2, and maybe let's call them f and g. And then we have a bunch of pullbacks. So in general, our input data is we have lots of spaces mapping to a single space, and then we take the pullbacks of all of them and get an enormous cube. And that cube, like functors of this form built out of stuff in that cube, is what we're going to prove, all the diagrams commute from. So in this case, this would be like our allowable arrows would be f star shriek up or down, f prime star shriek up or down, g and g prime. If we had x3, we would have more. We would have more possible things, but all the arrows would have to live in this cube, which makes sense if we want base change, because base change relies on pullbacks. So this is a way of starting with stuff in a cube and restricting our diagrams to a class that we have all of our tools available. Okay, great. So maybe you'll just look in this example. So this problem sort of boils down to, I don't know, G lower star, H upper star. And okay, one thing which will make it easier for me to write, instead of these primes, I'll just call this G when I write G lower star. So here we've got a G, here we've got a G prime. If I'm writing a sequence of words like this, I'm just going to write it as G, because if you interpreted it in the diagram, there would only be a unique choice for whether your G lives here or G lives here. So, okay. So this is like a thing to make our notation easier. And so I'll show you what I mean. So, we start with, all right, writing backwards. So let's write composition the correct way. So, we could start with f lower star and then take a h upper star and then take a g upper star and then take a f lower shriek and then, I don't know, blah, blah, blah. Okay, so what we get in the end is a string of n symbols. Okay, and our rules for manipulating these, like our valid isomorphisms, are going to be, we can switch these things if it's allowed, or we can switch these things if it's allowed. And you can see here, the reason why I've chosen to not look at the primes is that, this is G prime F star, and this is F star G prime. So if you, in your notation, ignore the primes, then you can sort of see that it looks like things are commuting. Okay, so these are our input data, our functors that we want to show that, and the problem is to show that all natural endomorphisms or natural automorphisms of these built out of these pieces are trivial. Right? That's, if you want to show that two paths agree and they're all isomorphisms, that's just going the whole way around, we can show that that's trivial. Great. So say we've got n symbols. I now want to describe how we can actually show that every endomorphism is trivial. So, and the key thing is that these operations only swap two things at once, right? So we've got a list of n symbols, and then we've got some operations which swap two things. Now, we're not always allowed to swap any two things. For instance, maybe we can't do base change on these two things, but we could do base change on these two. We can do a composition isomorphism on these. So like there's a restricted sort of set of moves you can do, but any move is just applying a simple transposition. So step one, encode these moves or isomorphisms as simple transpositions. So these are like, I plus 1 in the symmetric group on n elements. Okay, and so we can see that our two moves are determined by this data. Like if I look here and say, okay, do a transposition, there's only one valid move that we can do. Go here, do a transposition, there's only one we can do. I can't say, go here and do a transposition, and that's okay. Like it's not always defined, but any move is determined by its transposition. Great. Okay, so now we have transpositions in Sn. Now let's recall a definition of Sn. So, or a presentation. So this is generated by elements which we call sigma I, such that sigma I. Oh, I should say one more thing. Upper shriek. I am defining like a transposition, like if I'm saying that if I want to apply a transposition at this part, it just means do nothing. So this is a technical convenience to make this work. Yeah, so, but this definition may not make sense with that. Okay, so our relations in the symmetric group. Okay, so this says that all of our simple transpositions square to the identity, and this says that we can braid. So you can braid adjacent simple transpositions. So sigma I equals I plus 1. Great. So now the strategy is to just check that if we interpret moves as transpositions, that they satisfy the braid relations. Okay, so what do I mean by this? Let's take, say, I'm not sure if these are the correct order, but just as an example, say we switch these two things, and then we get H star G shriek, and then we switch these two things, shriek, and then we switch these two things. We could do that, or we could do it in the other order. And then finally switch those two. And so we see that this is a potentially non-trivial coherent statement that these braid relations hold. But in my instance and in general, you don't actually have that much stuff to check, right? If you want to check that these braid relations hold, you just need to check it for combinations of stars and shrieks, and that's something that you can do. And I believe it follows from the functoriality of this being like landing in two categories and having these compatible isomorphisms. But in general, like this is a checkable condition. For an arbitrary input data, you can really just check this. Okay, so what's the upshot to this picture? So
try to wrap it up quickly.
Oh, sure. So the upshot to this picture is any endomorphism here can be encoded as a bunch of simple transpositions. And the fact that it satisfies the braid relation is that it's encoded by a word in Sn, right? It's encoded by an actual element of the symmetric group rather than just a bunch of transpositions. And then you have some very nice rewriting rules in SN, essentially that if a word is trivial in the symmetric group, you can show that it's trivial by applying this and by deleting adjacent pairs. You never have to add extra stuff. And so because of that, you can show that, okay, you've got a word here in SN. You can show that it's trivial by other means. And then once you know that it's trivial, okay, that just tells you, okay, find braid relations, find things to cancel, and that will give you a witness for it actually being an isomorphism or being the identity. So yeah, like this encoding procedure, once you know that these things satisfy the braid relations, is all you need. Like you need to think a little bit to say why the words are actually trivial, but then you can, write down an expression in SN, apply braid relations, apply algorithms to actually do this, and you will get my diagram commutes. Like you can build a thing which shows that your diagram commutes.
I can train that.
Great.
Yeah.
Cool.
All right, so you're finished?
Yeah, I can finish.
All right, so let's thank the speaker. Any questions?